2022, question number 1. So this is about different fuels, so like usual, this you need to read, albeit quickly, but I'm going to jump straight into the first question. Draw the skeletal formula of 2,2,4-trimethylpentane. It's a pretty straightforward skeletal formula, shouldn't really cause too much trouble. My approach would be to draw the pentane chain first, 1, 2, 3, 4, 5, and then I've got trimethyl, 2 of them on the 2, 1 of them on the 4, 1, 2, so 2 methyls there, and 1 methyl on the 4, 1 mark in the back, good way to start. And then we have this blending of ethanol into our fuels. So E5 is 5% ethanol, 95% octane, E10 is 10% ethanol, 9% octane. Write the equation for the formation of glucose in photosynthesis from carbon dioxide. Fantastic. Okay, we all know how to do that. So we just go straight ahead and write out 6CO2 plus 6H2O gives me C6H12O6 plus 6O2. You know, marks that really are available to anybody. Then the anaerobic fermentation of glucose produces ethanol and carbon dioxide, and it wants the anaerobic fermentation of glucose. Fantastic. So it tells us that we have glucose, C6H12O6, becomes ethanol. Now ethanol is C2H6O. I'm going to write it like that rather than C2H5OH because it makes counting the atoms easier, plus CO2. Now probably you'll just be aware that it balances 2, 2, but you should be able to work that out relatively easily if you don't. Okay, any other combination is not going to give you the right number of hydrogens and carbons and oxygens over here. Then we have what looks very pleasing to anybody that opens this paper is a bond enthalpy calculation. Hopefully it won't be anything that's too involved, and it is calculate the enthalpy of combustion of an isomer of octane. Fantastic. Okay, so octane is the alkane, so it's C8, H, if this is N, this is 2N plus 2, so that's 18, plus O2 gives me carbon dioxide and water, so I need to balance that. So I'm going to have 8 carbon dioxides, 9 waters, and now my oxygens, I've got 16 oxygens here and 9 here, is 25 oxygens, so I'm going to do 25 over 2. Then I go ahead and I do the bond enthalpy calculation. So we're going to count up all the bonds. Now I'm not going to draw it out because I know that there are only, in here, there are only CC bonds and CH bonds, and it should be fairly easy for you to work out how many of each one. There's no hydrogen bonded to hydrogen, obviously. There's only carbon bonded to hydrogen, which means there must be 18 carbon-hydrogen bonds. And I've got 8 carbons. Now, that means that there are 7 carbon-carbon bonds. If you're not sure about that, you need to go ahead and draw it out and convince yourself that it is 7 carbon-carbon bonds. Okay, I can't have 8 carbon-carbon bonds if I've only got 8 carbon atoms. Then I've got 25 over 2 times my O double bond O. That's my one side, that's my reactant side. Over here, this should be now second nature, 16 carbon oxygen double bonds and 18 hydrogen oxygen bonds, given that each of these, so carbon dioxide contains 2 carbon oxygen double bonds and water contains 2 oxygen hydrogen bonds. All right, so from there, I just go ahead and put all the numbers in. So where's my data? My data is here. I can't quite get it on the same page. Maybe I can. Not quite. All right. So let's not worry about it. I'm going to go ahead and do 7 times carbon-carbon, which is 347, plus 18 times CH, which is 413, plus 25 over 2 is 12.5 times oxygen, which is 498. So that's my reactants, and I subtract my products from it, which is 16 times 805, subtract 18 times 464, which gives me minus, maybe you can see that, minus 5144. Minus 5144 kilojoules per mole. Oh, you can't see that though. There you go, minus 5144 kilojoules per mole. All right, then that is D done. So now we get this bit where it gets slightly more complicated. Assume that 1 litre contains 100 millilitres of ethanol. So E10 is 100 litres of ethanol, 900 octane. E5 is 50, 950. Fine. That's easily understandable. Then we're given the densities of each one. And we're given the combustion value for ethanol. And then it is, for both E5 and E10 fuels, calculate the energy in kilojoules released when 1 litre of the fuel is burned. Oof. All right, and you'll see that this calculation is 3 marks, so it's a little bit of an involved calculation. So we're going to think about it nice and logically. We've got to do it for both E5 and E10. I think it's just easier for me if I do E10 to start with. Okay, so E10. Now, E10 is, let's think, it's 100 centimetres cubed of ethanol, and it is 900 centimetres cubed of octane. Okay, and I know that the combustion of ethanol is minus 1276 kilojoules per mole, and the combustion of this I've just calculated is minus 5144 kilojoules per mole. And I want the total energy released in kilojoules when I do this. Now this is a volume, and this is an energy per mole. So what I really need is I need to know how many moles is 100 centimetre cubed of ethanol and how many moles is 900 centimetres cubed of octane, which is why I've been given the densities. So I can convert my 100 centimetres cubed into a mass because I know that ethanol is 0.789 grams per centimetre cubed. So this is going to be 78.9 grams of ethanol. Okay, so 100 centimetres cubed in volume is 78.9 grams. Then I do the same with octane. That calculation is a little bit more difficult. 0.703, 632.7 grams of octane. Okay, fine. Now I need to convert my masses into moles. So the number of moles of this is going to be 78.9 divided by the molar mass, and this one's going to be 632.7 divided by the molar mass. The molar masses you can work out yourself. I've already worked them out somewhere else. They are 46.068 and 114.224. Okay, so if I do that, I then get my number of moles. So 78.9 divided by 46.068 gives me 1.713. And this one is 632.7 divided by 114.224 is 5.54. So these are the moles now. So 100 centimetres cubed of ethanol is 1.713 moles of ethanol. 90 centimetres cubed of octane is 5.54 moles of octane. So then all I need to do is just multiply this number by this number to get the kilojoules. So the heat released equals 1.713 multiplied by 1276 plus 5.54 times 5144. So it is 1.713 multiplied by 1276 plus 5.54 times 5144 gives me 3068. Let's do 4 significant figures. 0 kilojoules. Does that seem like a sensible number? I mean, it is a litre of fuel, so I would expect quite a lot of energy to come out of it. All right. So then I can go ahead and put that in there. 30680. Then I just need to do the same calculation again, but now the only difference is I'm going to do it with 50 centimeters cubed of this and 950 centimeters cubed of this. So that is literally just the same calculation, just with those numbers changed. So it's going to be 50 times 0.789, which is obviously half of that. So it's going to be 39.45 grams. And it's going to be half of that number as well. So let's just do that. Let's do 0.713 divided by 2 is 0.86. And then this, I mean, I could do it, or I could just, you could just do 0.95 divided by 0.9 and then multiply it by your answer, 5.54, to give me 5.85. Okay, hopefully that was clear what I did there. I just used the ratio. I mean, you can do it yourself again if you want. You do 950 multiplied by the density divided by the MR, and you'll get that number anyway. Okay, and then you just put those numbers into here. So instead of 1.713, it's 0.86. And instead of 5.54, it's 5.85. And if you work these out individually, then you can just multiply by the ratio. It works either way. Okay, so 0.86 times 1276 plus 5.85 times 5144 gives me 31189. So let's go 3119. Oh, you can't see that. 90. My number is coming out slightly too large. It should be 31170. Probably just a rounding. Yeah, it's probably just this. If I change this word, if I change that to 47. Oh no, that's already stored it in the memory. Okay, never mind. Well, look. Maybe, I think that's fine. The rounding might be slightly off, but the idea is the same. Then, taking the energy released from burning 1 litre of E5 as 100%, calculate the percentage of energy released from burning 1 litre of E10. Fine. So, this is 100%. So what is this as a percentage of this? They don't come much easier than that. It is just going to be 30680 divided by 31190 times 100. 30680. And at this point, if you did get penalised for having the wrong round answer, you wouldn't get penalised here because they give you error carried forward. It gives you 98.4%. So, you know, you double the amount of ethanol and you get a slight reduction in the amount of energy that you get out. Fine. All the carbon dioxide released by the combustion of ethanol is offset by the carbon dioxide captured when the plant's grown, apparently. As such, the contribution from ethanol is not counted when the CO2 footprints of the E5 and E10 fuels are compared. Taking the CO2 produced from burning 1 litre of E5 fuel as 100%, oof, okay. Calculate the percentage of CO2 produced from burning 1 litre of E10 fuel. Consider only CO2 formed from the combustion of octane isomers. So that is complicated, all right? And it took me a little while of looking at this to really work out what it was that they wanted me to do. So they want me to take the octane produced from E5 as 100% and calculate they want the CO2 produced by the burning of octane in E5 as 100% and work out this CO2 from burning octane in E10. All right, so it's a little bit complicated. So let's just think. The octane is C8H18 plus 25 over 2O2 gives me 8CO2 plus 9H2O. Okay, and what it's saying is when I do E5, I get a certain amount of this, and when I do E10, I get slightly less than this, because in E10, the proportion of octane is lower. Okay, so in E5, it's 95% this, and in E10, it's 90% this. So I get a slightly lower amount. Okay, and in fact, I have worked out the number of moles. Okay, because I can go back over here and I can see that the moles of octane in E10 is 5.54. That's my E10. And the moles of octane in E5 is 5.85. Okay, and the moles of carbon dioxide is they're going to be 8 times each of those numbers. Okay, so I could do 8 times 5.54 to give me the moles of octane produced from burning octane in E10, 44.32. And I could do 8 times 5.85 to give me the moles of carbon dioxide, so moles of octane, moles of carbon dioxide, I was right the first time, produced from burning octane in E5, so 46.8. At this point I can double check that I get more carbon dioxide from E10. Hold on, I think something's gone wrong. What have I done wrong? So that was a good check to do, because really I should get less carbon dioxide from octane when I do E10. Oh, I've just done them the wrong way around. So I did that. The first calculation I did was E10. So I've just put these numbers the other way around. So that's 44.32 and that's 46.8. All these mistakes I make are all intentional, by the way. Definitely not just happening to me on the fly. And so then it says that, you know, 1 litre, fine, but really if it's all these ratios all carry all the way through. All right, so I can just do the molar ratio. So I can just do 44.32 divided by 46.8 times 100. And the answer is not going to surprise us, because if I do 44.32 divided by 46.8 and I times that by 100, what do I get? I get 94.7%. 94.7%. What I should get is 95%. That should definitely be my answer, because the composition of E10 is 90% octane. The composition of E5 is 95% octane. So obviously, I will get a ratio of carbon dioxide of 90 divided by 95. Oh, that's so. What am I talking about? And if I do that, oh, I was right the first time. If I do 90 divided by 95 times by 100 equals, 94.7. Okay. So I could have just done it like that. Sorry, I might have confused you there a little bit. So the amount of carbon dioxide produced in E10 is 90% of the total. The amount of carbon dioxide produced in E5 is 95%. So it's just the ratio of the two. I feel like that last question I didn't explain great, but I did it 2 different ways. Hopefully it makes sense to you. If not, there's not much I can do about it. Sorry.